Basic tenet behind Maxwell's gas law was that pressure times volume equals mass velocity squared. Okay, of course what velocity means gets a little more complicated in how we want to define mass, because eventually this becomes nRT. But we're not going to go into such detail in a moment. We're just going to show it on the chart. Here's pressure right here. And we say going from pressure to volume, we're going to be integrating upwards 3 times. So let's write pressure here. Got 1, 2, 3, dx, 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 and this equals energy. So we've gone up 1 integration of distance, 2 integrations of distance, 3 integrations of distance, and of course now we're defining a volume. Okay, now let's look at the other part of this. Mass velocity squared. Well, here's mass. We go up 1 velocity, and then we go up yet again another velocity. So this tells us that both of these instances, pressure times volume equals energy, and mass velocity squared equals energy. Okay, that's one familiar theorem. Of course, it's an axiom. Okay, let's look at yet another one. We know from pulses on ropes that velocity equals the square root of tension over mu. Well, this could also be rewritten as the square root of force over mu. The tension is just the force in the rope. Okay, well let's expand this out a little bit. So this says velocity squared times mu equals force. Well, here's mu, here's 1 velocity, and here's 2 velocity. And indeed it lines us up on the force box. Okay, let's look at one from a mass spring problem really quickly here. We have a mass and a spring with a K, and we set the mass in motion. And we know that its frequency equals the square root of K over M. Okay, then it tells us that frequency squared equals K over M, or mass frequency squared equals K. Well, the operations tell us here's mass times 1 frequency, and here's mass times frequency squared, and indeed it winds us up on K. Okay, now we'll show some simple relationships here. Here's a nice simple one. Force equals Kx. So K times the distance is force. Okay. Pressure times an area is force. So that would be what? The double integral of pressure, dx dx equals force. Okay, here's one we can get. Force over velocity is impedance. We'll just use the symbol Z. Okay, here's another one that's sort of interesting. Power over velocity is force. Okay, here's another one yet. Force equals the time rate of change of momentum. Well, here's mass times the velocity. And indeed, the time rate of change of momentum winds us up on the force box. Okay, now let's talk about what is acceleration. Well, the units for acceleration are meters over seconds squared. What does it mean? Well, we just hinted at it. It means d dt of velocity. Okay, what is the d dt of a velocity? Well, that basically tells us if we start at a spot like mass, we will have gone up 1 unit over 2. Not necessarily in that order. So, here's an acceleration. Up 1 over 2. Now we're not limited to just an acceleration from the mass box. Clearly you'd get an acceleration from here up 1 and over 2, the spring constant k. And these all have true meanings. Okay, let's look at curl, also known as circulation. Its units are meters squared over seconds equals curl, also known as circulation. Well, what does it mean? Well, it's the double integral excuse me, dv dx, and not necessarily in those order. What does it tell us operation wise? It says you go up 2 units and over 1 unit. So the curl of mass will be up 1, 2, over to here. So here's a case of a curl. We'll just leave it as dotted like that. Okay. Now, before we end this discussion, we want to make an observation here. We had our rules that told us what went on between the relationships of boxes. So in order for a box to exist, it had to have these relationships. So that tells us we can stand back and look at the chart and see that elements must have infinite integrals and derivatives in time and space, or the element itself cannot exist. And that's it for now.